What if I told you ninjas that you could find the derivative of an inverse function at a point without even having to know what the inverse function is? If you don't believe me, stick around because you're going to see for yourself in just a few minutes. I'm sure many of you have tried finding the inverse function of f here. I'm guilty of this too, where when you swap x and y for the equation x equals y cubed plus y, good luck trying to solve for y by itself, right? It's a bit of a headache. But we can skip that for now. And if we do a little bit of work, we can use a really cool theorem to save a ton of time here, and you're going to see in just a bit. By inspection, the first thing we have to make sure of is, do we even have an inverse function? It's pretty simple on a graph, right? This passes the horizontal line test. The next thing I need to do is figure out what the derivative function is. That's going to be 3x squared plus 1. And now I want to look at the domain of this derivative function and ask myself, can it ever be 0? Well, we know it's a concave up parabola with a local minimum and global minimum at x equals 0, which would give me an output of 1. And so specifically for all real values of x, we know that the derivative function is always going to be strictly greater than 0. Now, why is that important? Well, one of the conditions of using this theorem is that at x equals 2 specifically, the derivative function cannot be 0, and also the derivative function needs to be a continuous function, which by inspection we know it is. So with those conditions being met, what the inverse function theorem tells us is the following. So for a constant a, which in our case a is 2, if you're in a neighborhood of a, meaning really, really close to a, including being at a, this is telling us that the inverse function theorem has a property where we have local invertibility near a. So in other words, we can actually save ourselves a lot of time. And for this expression here on the right-hand side, the inverse function at a means that we don't even have to know what the inverse function actually is. Because if you remember, for the inverse function at 2, instead of having to solve for an expression of x and y, all we care about is because the inverse function is undoing or reversing the original f of x function, this is telling us, okay, we just got to find our real values of x, because in this video I'm only dealing with real values, such that the output is 2. Now, this is a very elementary problem to solve, and you can do this on your own and verify, but this only has one real root by inspection at x equals 1. So this is telling us that for the inverse function at 2, we have a value of 1. And then when you plug it into that inverse function theorem expression I gave you above on the right-hand side here, this denominator simplifies to now simply just evaluating the derivative function at a value of x equals 1. And so when you plug that in, you get a really nice and easy fraction to work with, giving you this answer